that's a possibility. That when the black hole gets to the Planck scale, it slowly starts sending stuff. The problem is that the amount of information it needs to send depends on the mass of the initial black hole, right? Which could be arbitrarily big. So depending on the mass of the initial black hole, it might take longer time because you have to encode that information into quanta that have a total energy, which is the Planck scale. It's a small amount, relatively small amount.
I see.
Yeah, that was one scenario that people had discussed previously. For some of the things we are going to talk about, we will not need this full evaporating black hole.
But does those discussion need something go beyond semi-classical?
Yeah. Because you need to say what happens at the very end of the evaporation. So there is a version of this puzzle which does not involve knowing what happens at the end. So we'll discuss it today. This version is what Hawking discussed.
This version?
Yeah. Okay. Yeah. Okay, so today we are going to start discussing the second law. We are going to continue the discussion of black hole thermodynamics. So the first lecture was supposed to be all of black hole thermodynamics, but in more modern slant and with some recent results, including the result of the second law that I'm going to start explaining now. Okay, let's see. Maybe it's not on. Can you hear me now? Is it better? Put it up. Now? That's better. Okay. So we'll continue the discussion of black hole thermodynamics. So now we are going to discuss the second law of black hole thermodynamics. And this is related to a thought experiment that goes back to the beginning of the subject of black hole entropy and so on, which was the following. So people knew that there were black holes and they had horizons. And well, energy is conserved in the outside universe, so you can send energy to the black hole. The mass of the black hole increases. But Wheeler asked Bekenstein, what if we send entropy into the interior of the black hole? Does the entropy of the outside universe decrease? So naively, it seems that they might decrease because you send the entropy inside. So that led to Bekenstein to suggest that the final entropy of the black hole should be the area over 4G Newton plus the entropy outside. Okay. So that this entropy decreases, but the area increases by more than that amount. And today we'll try to see under what conditions that happens. Okay. So imagine we are very close to the horizon. And we have some matter that we are going to send into the black hole and will fall into the black hole. So I mean, if we draw in this Penrose diagram, the matter is really following this trajectory. Okay. But this matter has some entropy, let's say S matter. And it also has some energy. And some energy which, some mass M. Or we could also equivalently think in terms of the Rindler energy. So let's say we are looking at this in the near horizon geometry. That would be some Rindler energy, which we can call E tau. We can also call it K, just to make contact with the previous lecture. If we think of the Rindler density matrix outside as being given by, let's say, e to the minus 2 pi k. Okay. This is not exactly the k that Hong discussed. The k that Hong discussed had a rho minus 1. K is the boost generator that generates this boost, and then it's exactly the one that Hong discussed. Okay. Very good. So now if it has this mass, so m is the mass of the matter, and E is also, and K is also the energy of the matter. Then the change in the area over 4G Newton turns out through the Einstein's equations to be of the form 2 pi this E tau, the Rindler time normalized as we were discussing, or 2 pi k, or the energy measured with respect to the ordinary Rindler time divided by the temperature of the black hole. So this is the energy of the matter that we are sending, not the energy of the black hole. Okay? This just follows from the Einstein equations and the near horizon physics. We'll later discuss it in more detail, and we'll also even derive it. Okay. Now, so that's the change in the area, and this change should be bigger than this entropy, than the entropy of the matter that we threw in. Therefore, in order for the entropy to increase, what we need is that 2 pi times this Rindler energy, which let's call it k, should be bigger than the entropy of the matter. Okay, so this is the k of the matter and the entropy. And it was a so this is something that we need to be true. Okay, the question is this true? Couldn't we imagine some matter that carries a lot of entropy but not much energy? So, for example, you could have a particle that has many internal degrees of freedom. So the entropy will be like the logarithm of the number of internal degrees of freedom, but the mass is fixed. We could make that number very big, and it looks like we might violate this condition. Okay. So for some time, people thought that, well, Bekenstein had actually further simplified this. He said, well, this is some energy E that occupies some size R, and in order to, so the largest value of k we could have is when we put it very close to the horizon. And so this goes like E times R, right? And then was this bound, which was called Bekenstein bound. And people tried to argue whether it was true or not true, and so on. So a better way to think about the bound is to think in this term. So we're not going to have the old way to think about it. But the important point is that this is a bound that is supposed to be obeyed by quantum field theory, not by gravity. So G Newton disappeared from this bound. And now this is some property of quantum field theory. And so the question is whether it is true or not true. And I just gave you a vague argument that it might not be true. Okay. So for some time, people thought that this was a constraint on quantum field theory. But actually, we'll see that that's not the case. So we're going to give a general argument that this is indeed true. And this is an argument that was given by Cassini. So the correct version of the argument is that we are going to calculate the entropy of the matter the energy of the matter outside, and this should be bigger than the delta S, where delta S will be the entanglement entropy of the state of matter that we have. We have the Rindler wedge, and so we have some state in the outside of the Rindler wedge. There is some state of matter. It will have a certain density matrix rho, and it will have a certain entropy. And then we are going to compare the entropy that you have in the case that you have for the state that you have versus the one you have in the vacuum. Okay, so that difference, the diversions will cancel in that difference, and you will get some delta S. So this is a finite quantity. And then we'll similarly here consider delta K, where K is the boost energy that you have for the matter state, minus the one in the vacuum. And the one in the vacuum, you can say it's 0. So putting the delta here is not very important, but it was important to put it here. Okay. So this is the so-called Cassini-Bekenstein bound, and we'll explain why it is true. Okay. So the idea of the proof is the following. So first, we'll define some quantity which is called relative entropy. And this is a quantity that can be defined in any system. So it depends on two density matrices. So you have some system and you have two density matrices, S and rho and sigma. And then you construct trace of, this is just a definition, trace of rho log rho. So this looks like minus the entropy of one of these things, minus trace of rho log sigma, okay? Now this quantity, roughly, you could view it, if you view it as sigma, as if you view log of sigma, some kind of Hamiltonian, this quantity can be viewed as minus the log of the free energy, right? It's like a free energy, so entropy minus energy. Now, the nice thing about this quantity is that for any two density matrices, it's automatically positive, okay? And furthermore, it's well defined even for type 3 algebras and so on. In those cases, this rho and sigma do not make sense. It has to be derived in a more sophisticated way. I don't know if Juan is going to discuss the derivation of this, but it's a quantity where all divergences cancel and so on, and you get a well-defined quantity. And furthermore, you can that can be proven that it's always positive. As an exercise, you can try to prove it that it's positive. The rho and sigma are diagonal. You can sigma, you can argue it's positive. And furthermore, this quantity has an information meaning. It measures how easy it is to distinguish the density matrix rho from the density matrix by repeated experiments. It gives you many copies of rho, and you're trying to do experiments, trying to see whether it's really sigma or not. Whether it's sigma instead of rho. If this quantity is, the larger this quantity is, the easier it will be to distinguish between the two. Okay, very good. So we have this that is positive. And so now we simply, so the proof of this is very simple. All we have to do is rewrite this in the following way. So rho will be the density matrix of the state we have, okay, what we have. And sigma will be the density matrix of the vacuum, okay? And it will be equal to e to the minus 2 pi times the boost Hamiltonian. I'm normalizing the k differently from what Juan discussed. He didn't put the 2 pi, but so this k normalized this way is literally the boost energy the way we normalized it before. And then, so if you now these quantities, you find that S of the state we have, right? And then, okay, and then this term here is minus the 2 pi k, so it's plus 2 pi k, the expectation value of what we had for the vacuum, right? And now we sort of add and subtract the term that contains sigma log sigma, and that one of those subtractions we call it the entropy of the vacuum, and the other one we can call it the minus 2 pi k of the vacuum, right? And then we get this difference between the same difference we had here between the two terms, okay? Maybe I should. Oh, you cannot see. Oh, okay. Okay, very good, very good. Let me. Oh, that's not too good. Let me rewrite this important formula here. So the relative entropy is minus S, so that's the first term, plus 2 pi k. Okay, that's this term. And now we add and subtract. Trace of rho vacuum log rho vacuum. Okay. This is k because this quantity here was essentially k. Okay, up to an overall constant. Because here this is an unnormalized density matrix. Okay. So if we normalized it properly, we are subtracting some constant, and that's why, which is essentially this, and that's the one we are adding and subtracting, and that's also the entropy. So we will get. We are adding one. We think of it as the entropy as vacuum, and the other one we think expectation value of 2 pi k, the expectation value of k in the vacuum. Okay. Is this clear? Or this should be clear derivation. I mean, we are thinking of this as either the entropy, or if you think of this as the modular Hamiltonian, then this is the expectation value in the vacuum. And therefore, this is minus delta S plus 2 pi delta K. And we concluded this should be bigger or equal than 0. And that's the quantity that we wanted. That's the inequality that we wanted. Okay. Good. So this is is true, and it's true for any quantum field theory. So there is no constraint on the quantum field theory, and that shows that there was something wrong about the argument. I showed you a counter. I argued before that it should be violated. Let me repeat the argument. If you send the particle, if you have particle that has many flavors, then it looks like it's the logarithm of the number of flavors, and the mass is fixed. So we have a contradiction. So as an exercise, you can try to understand how that contradiction is resolved. Maybe I just give you a hint. It's important they are subtracting here the entropy of the vacuum. And so even though you said you had the particle that has all these flavors, if you have here only the right side of the Rindler wedge, you have some finite temperature state. And out of the vacuum, you will be creating these particles of the many different flavors. So it is possible that even in the vacuum, you will have some particles of this, some various particles, not just a single particle. And once you consider this more complicated situation, well, quality is true. So the argument that I given for the calculation of the entropy would be incorrect, okay? Because you have many more particles. Okay, very good. So one good news about this is that there are about 1,000 papers trying to discuss various aspects of the Bekenstein bound, either looking at specific systems or arguing why it's true or not. You don't have to read any of them. You just only have to read this cynic paper. And also there are papers that continue to appear on this that they don't know that this paper has been written. Okay, so this is one interesting situation where from black hole thermodynamics, we came to some true property of quantum field theory. One question is whether we can do the opposite. So can we really prove can we really prove the second law? So we don't yet know whether the second law is true or not. So let's discuss a bit more the proof of the second law. So the second law was classically proven if you ignore the S entropy outside and you only consider the area term, and you consider purely classical evolution of black holes, then it was proven by Hawking a long time ago. It's the area theorem. But once you include the quantum corrections, it's not so clear. And I mean, we have to include quantum corrections if we are going to treat semi-classical black holes, because black holes can evaporate, the area will decrease, and they will emit radiation. So you have to make sure that the entropy of radiation grows more than the decrease of the area. Okay. Good. Now, the ingredient that comes into proving the second law, the second law, including the quantum corrections, was proven by Wald, by Aaron Wald. And I will sort of sketch his argument. So it involves two elements. So let me just mention the elements, and then we'll put them together. So one element is a sort of quantum information inequality, similar to the one we were talking about there. And it's the following. So imagine you have two systems, and the one is a subsystem of the other. So we have subsystem 2, which is smaller, and subsystem 1, which is bigger. Then we can consider the density matrix on the bigger subsystem, and then we can take that same density matrix and reduce it to the small subsystem by tracing something out. So then we can construct the relative entropy. So the relative entropy that if we have two such density matrices, now for subsystem 1, okay, so these are both defined for subsystem 1. We could put a 1 here. Then this will be bigger than the relative entropy for subsystem 2. Okay. So this, I emphasize, these are two arbitrary density matrices for subsystem 1 for the big one. These two are come from reducing these two density matrices to the smaller region. Okay, that's how we define these two. And the non-trivial inequality is that this part is always bigger than this one. And proving this is not very simple. It's proven by Liv and Ruskai. They actually prove something else, which is called strongest additivity. But you can intuitively understand why it should be true if you think of this quantity as telling you roughly how easy it is to distinguish these two density matrices. So if you have less operators, it will be available to you because we are in a smaller subsystem. It will be harder to distinguish them. So that helps you remember in which direction this inequality was if you don't remember it. So that's why you might expect it should be true. So that's element number one. Element number two is basically the same thing that Hawking used, and it's the Ray-Choudhury equation. So this is just an equation. This has Einstein's equations, some component of Einstein's equations. So the idea is that you have a bunch of light rays that are coming from some surface. In this case, the surface is the horizon at very late times. You go backwards in time, and you follow light rays that, let's say, from a cross-section of the horizon are emanating backwards in an orthogonal way to the surface. So then you can define something that is called the expansion, which you take the derivative. Oh, sorry, one more thing. So these are a bunch of null rays, and null rays can be characterized by their affine parameter with some way of parameterizing the light ray. And we take the derivative with respect to the area, with respect to this affine parameter. Think of this as some null coordinate along the null ray. And so we can see how the area is increasing as you move here forwards. This is called the expansion. This is just a definition. Then Einstein's equations tell us that the derivative of the expansion with respect to lambda is equal to some term, so a bunch of terms that are all negative. So d minus 2, so it's some constant depending on the dimension. There is some piece that has to do with how these light rays shear each other and so on. And then there is a piece that has to do with the stress tensor, the lambda directions. Sorry, 8 pi g Newton. So this is a piece that comes from the curvature part of the Einstein equations. Well, all of this part comes from the curvature part of the Einstein equations, and this comes from the stress tensor. Okay, so that's an equation, and it's just a component of the Einstein equations, and it's a very useful component that is useful for proving various things. For example, even also the Penrose singularity theorem that we discussed is also proven using mainly that equation. So now we will consider the horizon. So we start from the infinite future, where we think we have a system at equilibrium, let's say a black hole in equilibrium. And so the area is not expanding in the future. So theta here at infinity is, so when lambda is equal to infinity, is equal to 0. So it's not expanding. And then we have, let's say, some time 2 and some time, let's say, earlier time 1, right? And what we want to argue is that the area, well, first of all, the area of 2 is bigger than the area. Well, if it was the classical problem, we would try to argue that the area of 2 is bigger than the area of 1, okay? And what we really want to prove is that the generalized entropy of 2 is bigger than the generalized entropy of 1. Very good. So let's first look at the change in areas. So we have area 2 minus area 1 over 4 g Newton, okay? We can rewrite this essentially in terms of the expansion. So let me assume that just for the sake of this argument, that the change of the area is going to be relatively small between 1 and 2. Okay, so I'm going to treat those changes to first order. So we have the expansion between 1 and 2, and I'm going to pull out the area, the constant area outside. So this is some kind of mean area between 1 and 2, and we'll write the expansion. So this is just simply from the definition. Okay, haven't done anything yet. Then we again rewrite this as minus area times integral between 1 and 2 d lambda, and then we write this in terms of the derivative of the expansion. Okay, so here we are using, so if we do this is a total derivative, so if we integrate it, we get the expansion, which is what we had here, the minus sign. And at infinity, we are using that this is a horizon at equilibrium, so it's not changing. Okay. Notice the horizon is something that is defined knowing what will happen in the future. So we go from the future to the past. Okay. It's, you need to know what happens in the future to find where the horizon is in the past. So that's a side comment. Okay, so we have this, and now we will use the equation we had here. So we'll put this term in the left-hand side and all of this in the right-hand side, right? So so that implies, so you'll see all these are negative terms. Let me switch the sign. What we had there is essentially minus this quantity, right? And so it will be, whatever this is, it's going to be bigger than just the stress tensor, okay? So we'll just write simply that this will be bigger or equal than just the contribution that comes from the stress tensor. So 2 pi, let's say the g Newton cancels, and so we get just a factor of 2 pi, and integral between 1 and 2 d lambda, integral d lambda to infinity, d lambda prime, d lambda prime, okay? Now, if we want to get the Hawking theorem, we just simply say that this is bigger or equal than 0 by using the null energy condition that says that d lambda lambda is bigger than 0. So we derive now the Hawking argument. We derive the Hawking theorem. Now, we don't want to do that because we want to include the quantum corrections. And so we will not do that yet. So let's do a little more now. So we'll take these expressions and integrate by parts. So we'll first split the integral into 2 pieces. So 1 to infinity, let's say d lambda, integral d lambda to infinity, d lambda prime, d lambda lambda prime. And this one we will subtract lambda 1. And then we integrate. So if we integrate this, so we integrate by parts, the derivative acting on here will give us t, and we'll get a factor of lambda minus lambda 1, right? So those will give a term which 2 pi, well, there is a term proportional to the area, and then some integral, for example, between 1 and infinity. Let's see. Yeah, the lambda minus lambda 1, d lambda lambda. Okay, so this has the form of boost energy, relative, so measured relative to the point 1. Okay, so it looks similar to the Rindler, the expression for the energy in Rindler space. So let's go back here to Rindler space. So if we have, so the Rindler energy can be viewed as, let's say, integral over this distance rho times the ordinary energy, right? So rho times the ordinary energy is like angular momentum, right? Distance. Rho times the ordinary energy measured with respect to time. So choose to measure, in which case we will have the integral dx plus x plus t plus plus, okay? Between, let's say, plus or minus infinity. Or, well, if we just consider the matter that can fall through this region, then it's from 0 to infinity. And that's what we get over here. Now, so I'm going to now present a simplified version of the argument, where we're going to think of this as approximately given by Rindler space. Okay, you have to be a little more careful. It's a little more complicated if you consider the black hole case, but we're going to think of this as a Rindler horizon. So here, in the far future, we have Rindler space with gravity, and then we had some matter that was falling in, and we're falling back those light rays, and we are going to then argue for that particular case that this increases. So this is like a toy model. Now, we made a simplification. But the point is then that this quantity that is appearing here is just the Rindler energy E1, okay? The E1, so let's say E tau, let me call it K, K1. So the Rindler energy measured with respect to point 1. And then there was a similar integral that we do with respect to point 2. And so the net result is that area 2 minus area 1 over 4g Newton is bigger or equal than 2 pi e tau 1. That's the one we computed, and then we have e tau 2. Oh, I was calling it k. K1 and K2. OK, very good. And then, so now let's compute the full entropy S2 minus S1, right? It has a piece which is this change in area, delta area, well, A2 minus A1 over 4g Newton. And then there is also a piece that is the S outside 2 minus S outside 1, okay? And now we insert these quantities, and we find that we will get the, yeah, so if we insert that quantity, we just simply get the relative entropy S1, so S rho 1 1 minus S rho 2 rho vacuum 2, okay? Where, remember, the relative entropy, as we saw here, was a difference between, where we have here. It's delta K, so the K of the state we have minus the vacuum, minus the entropy of the state we have minus the vacuum. And this is indeed what we have here. So we have the K of the state 1 minus the entropy of the state 1, right? That combined into this. And then here, this minus 2 plus this one combined into the relative entropy here, okay? But then we use the fact that we mentioned that those are positive, so this is bigger or equal than 0. And so we've then argued for the second law in this particular case. OK, very good. So this argued for the second law in the case of Rindler type horizons. That was the first paper that Aaron wrote, and then he generalized that in the case of black hole horizons. I'm not giving you that argument. You can read the paper. It involves some other new ideas. So now we've gone in the other direction somehow. From properties of quantum field theory, we went to black hole thermodynamics and established the second law of black hole thermodynamics in the semi-classical case, which was an open problem for many years. And what we used, so what did we use? So we used relativistic quantum field theory. So quantum field theory, that's one element we used. And then we used also the semi-classical Einstein equations. I should also mention that you can include curvature, so higher curvature corrections in a perturbative way. So when the higher curvature coefficients are relatively small in the semi-classical expansion. And even in that case, the generalized second law holds. And you have to include these higher curvature terms in that expansion because, as we said, when we go to one loop, we should consider at least the R² terms. OK, so that's good. And in particular, the second law did not impose any constraint on quantum field theory. Okay, there was a long time where people thought that maybe there is some constraint on quantum field theory, maybe there is some miracle that happens, or there are many papers, again, many papers talking about various cases of the attempts to violate the second law and something goes wrong, and but now we know from this type of arguments that it should always work. Okay. Very good. Also, there is the idea that perhaps the second law might constrain quantum field theory and will be a constraint on the kinds of quantum field theories that we can couple to gravity. So these people who think about the weak gravity conjecture and related ideas sometimes have had that hope. So that will not happen as long as this is valid. So it might be that because you might have a quantum field theory that has, let's say, you start increasing the number of flavors or the gauge of the rank of the gauge group too much, and at some point these semi-classical Einstein's equations might break down. So then that might be what breaks down. But there is no easy argument that from the second law will give you some weak gravity constraint, at least as presently understood. Very good. Now, for many of the things that we will discuss, the similar ideas were used, and in particular, a conjecture that has been used a lot, and it implies, it also implies this proven conjecture in general, is the so-called quantum focusing conjecture. So I'm only going to state it just so that you know what it is. Also because it's so similar to the classical focusing conjecture, or classical focusing theorem. So we had this this equality, right? And we noticed that all the terms in the right-hand side have the same sign if the null energy condition is obeyed, which is true classically. And that implies that light rays are always focused. So matter always focuses light rays, never defocuses them. That's classical physics. In quantum physics, we can defocus them if the stress tensor, the null components of the stress tensor might be negative in some places. Okay, so the quantum focusing conjecture is the following. So you define a sort of quantum expansion. Again, the same setup with the light rays and so on. The only difference is that we are going to change what we mean by the expansion. So there is a term that is just the derivative of A with respect to lambda. I don't remember. There was a G Newton here. Yeah, 4 G Newton. Plus a similar derivative. Derivative with respect to lambda, not just of the area, but of an expression similar to the generalized entropy. So we take any set of light rays. They don't have to be a horizon or anything. And then we construct this quantity, so the area plus the entropy outside. And the idea is that we define this. And this is just a definition. And the quantum focusing conjecture essentially says that the derivative of this with respect to lambda is less or equal than 0. Okay, so that's the idea. So the basic point is that by adding this entropy outside, so when this term is negative, the entropy term will be positive enough that it will be negative. This quantity will be negative. If you assume this implies a condition on the stress tensor, positivity condition on the stress tensor, which says that this is bigger. I'm going to write this schematically than the second derivative of the entropy outside. Okay. Again, I'm not going to go into the details of this. I'm only stating this relationship. Again, there is a 2 pi here. So this is a quantity, again, in quantum field theory, which you can prove, and it actually was proven in quantum field theory that this inequality is obeyed. It's called the quantum null energy condition. So this is some evidence, if you wish, in favor of this, in the sense that this implies something that is true, but we don't have a general proof of this quantity. So, yeah. Okay, very good. So in summary, so yeah, questions, yeah.
With the definition of this factor theta, could you actually normalize it by normal?
1 over a, yeah. Apparently, it's convenient to put 1 over a. Yeah, one might have thought that one needs to divide by the generalized entropy. But this is something that makes this somewhat intensive along the light ray. So along this congression of D6.
But we know this, the other one is not correct.
I don't know that it is not correct. So maybe it's known. But yeah, so this one is, well, with this definition, it implies this true quantity. But this true inequality is implied in the regime where it expands. There's very little expansion. Well, I think you will have trouble with the other. I mean, you could have the entropy outside could be very, very, very large, right? You could have like an infinite region. So then this will go to 0. Yeah, let me think about it. Maybe I'll answer for next time.
Also,
Yeah.
should we consider this quantity to be associated with a surface, or should we consider it to be associated with a region?
Very good. Yeah. So this is supposed to be associated. First of all, we have some null rays, right? And then we have some region that goes between an arbitrary point and the null ray. Okay. So it doesn't have to be the ADS boundary or anything. So any region in the box. Of course, if the null ray is supposed to hold up to the light cone, right? So if you get to this point, what happens here is that the entropy term becomes very, very small. This one goes to minus infinity. Yeah, so it's supposed to hold in these situations. Again, it's not proven, so it might be that once you try to argue, you need to anchor this to a boundary or something. Okay, so let me just summarize. So are there any other questions? Yeah.
Is there some kind of physical intuition for what this data is?
Well, other than the thing that makes sure that the generalized entropy will have the second derivative for a given sign, I don't know. Yeah. Okay. But well, we've seen that this combination of area plus entropy is a nice combination. So. Okay, so we basically what we did so far was to, I just remind you, we noticed that when you have a black hole, a peculiarity is that the black holes have, near the horizon of the black hole, the time translation symmetry at infinity acts like a boost. So that's something that is very important for many things. In particular, it's related to the fact that we have this temperature, we have Hawking radiation, and that's related to the fact that we can only see, we restrict all the fields to be outside the horizon. Then we reviewed the Euclidean black hole and thermodynamics, Euclidean black hole thermodynamics, the first law, and now we reviewed the second law. So all of these results are establishing what we can call semi-black hole thermodynamics, including semi-classical physics, including quantum corrections, black hole evaporation, and so on. Okay, so now we'll discuss in more detail a certain. So what we discussed so far has to do with, so we have the black hole and black hole thermodynamics and so on apply for observations that are outside the black hole. It's saying that the interior of the black hole obeys the laws of dynamics, and so on. Now, there is a certain influential hypothesis that we can call a central dogma. Dogma in the sense of assumption. And we don't know whether it's correct or not, but the assumption is the following, that if we make observations outside the black hole, so we have some black hole, and we make observations purely outside, then the black hole can be replaced by some system of qubits, some quantum system, qubits, with some Hamiltonian H that it makes them evolve in a unitary fashion. And the number of qubits should be less than, should be of the order of the area of the entropy of the black hole, so area over 4G Newton. Okay. Okay, so here there are a couple of things that are non-trivial. So one is that the number of qubits is finite, that you need to describe the black hole. We don't need to add an infinite number of degrees of freedom at the black hole horizon, only a finite number. And then the other non-trivial point is that this evolution outside will be unitary. So if this is true, then the black hole as seen from the outside will evolve in a unitary way. Okay? So the laws of quantum mechanics will also be obeyed. Now, sometimes people talk about black hole complementarity, which includes this hypothesis, but also it includes some statement about the black hole interior. Here we have not made any statement about the black hole interior, and we'll make more precise statements about the black hole interior later. But for now, this is just, we are restricting to observations outside, and for all observations we can do outside, the idea is that you can do this. Now, this is a property that is not obvious in quantum gravity. And in fact, there are some people who think it's incorrect and some people who think it's correct. So let's discuss first some evidence in favor and then some evidence against. Okay. So the evidence in favor, so this is evidence in favor. So 4. So it's just the fact that black hole thermodynamic works. I would view it as evidence in favor. So if you could throw entropy inside the black hole and disappear, so why would the entropy increase and the laws of thermodynamics hold? Also, the fact that black hole entropy in string theory works in the sense of giving some microscopic counting of certain black holes in certain theories. So you can find the states and count them and give you an entropy, which is area over 4G Newton. Then also ADS-CFT. ADS-CFT can be viewed as a more refined version of this hypothesis, where you have some ADS universe, and let's say you have a black hole inside, and you replace the whole interior of this universe, including the black hole, by some theory, then some CFT that lives beyond the boundary. And in this case, you know what the H is, so the H is the H of the CFT. Okay? But again, this is again a conjecture, right? So it might be that ADS-CFT is wrong in quantum gravity for some reason, and so it would not be true. But I view it also as evidence for this hypothesis. And now we'll discuss some evidence against, so or some arguments against. And there is the famous argument by Hawking against this idea. I'm erasing with the wet. Yeah, it's not a good idea. Try to erase. Okay, so what's the argument? So the argument by Hawking involved the evaporating black hole. So remember the Penrose. So he imagined the Penrose diagram roughly of this form. So we have Hawking radiation out of the horizon. So this is a black hole that formed from collapse, from a state with low entropy, let's say a pure state, just to make the argument simpler. There is Hawking radiation that comes outside. The Hawking radiation has some partners that go inside, or more precisely, by if we only look at this part of the space-time, which is what the part of the space-time that the asymptotic observer has access to, this observer will only see part of the overall state. So they will not see the interior. And when you trace out the interior, so you'll get some entropy here. So we get from pure states to mixed states. And okay, so and that is inconsistent with unitary evolution, because if you think of this as the fine-grained von Neumann entropy, we'll discuss that a little more. But so the entropy is defined as trace rho log rho. Then this entropy is invariant. So if you have some rho prime where it differs by rho by a unitary transformation, then because of the cyclicity of the trace, that's the same as S of rho prime. Okay. So the entropy should not change under time evolution. This fine-grained entropy should not change under time evolution. Okay, so that is some argument against. Now, the problem with this argument is that it involves the endpoint of black hole evaporation and exactly what happens with the endpoint of black hole evaporation. So people have tried to fix this by modifying the endpoint of evaporation, which is a place where you do not know what happens. Okay? So Page had a better version of this argument where you don't have to think about that. You notice that there is a contradiction before that point. So for that, we need to discuss the entropy of radiation and the black hole by separating the black hole from the radiation. So we imagine that we have a black hole. Imagine drawing some imaginary surface around the black hole. And so radiation comes out, and we'll discuss either the black hole system, which is whatever lies to the left of this, or the radiation system that is whatever lies to the right of this. So we're going to imagine separating these two things. Now, you might think that this is somewhat vague. If you want to make it more precise, you can think of this as an ADS boundary and coupling that conformal field theory to some external system that, let's say, contains no gravity. And then this exterior could be that region without gravity. That's a way to make this more concrete, more well-defined. But we don't need to do that for these arguments. Okay, so the idea is the following. So you now, because you are not infinitely far away in flat space, you can compute this entropy, the entropy here outside, as a function of time. So you can imagine that the black hole is evaporating. So let me draw a situation where we would have a black hole evaporation in ADS. So there is the black hole here. It's emitting radiation into some exterior part, some part that is not contained within ADS, some external non-gravitating system, sometimes called the reservoir of radiation. And then we can compute the entropy of this reservoir at different times. So we compute the entropy of this region here. Or we could even compute the entropy of the black hole at earlier time. So if we compute now the entropy of radiation as a function of time, as the black hole forms and it starts emitting radiation, so actually it was a black hole that was forming, the entropy starts increasing and will increase monotonically until the black hole evaporates completely. Okay? This does not have to be a straight line, but it has to be monotonically increasing. Okay, so now on the other hand, we form some black hole, that initial black hole that had a given area in the beginning, and the area of the black hole slowly decreases as the black hole evaporates. Okay. Now, in the beginning, when the black hole is very young, it's emitting radiation which is in a mixed state. But well, it could be that that state is entangled with the remaining degrees of freedom of the black hole. Okay, so that's no contradiction. It will happen with, with a piece of coal that is heated up and then it slowly cools down. The same thing would happen. But then, at a certain point, these two lines cross. This is called the Page time. And when the two lines cross, then we have a problem, because we cannot say that the entropy of this radiation is due to entanglement with the remaining black hole degrees of freedom. Or we have a problem with that central assumption that we had, or central dogma, that says that the number of degrees of freedom of the remaining black hole should be proportional to the area, right? So we have a problem. And so we have a problem in a regime where semi-classical physics is well defined, okay? So something new should happen at this point, okay? And semi-classical physics is well defined. We cannot appeal to the endpoint and so on. So this is the page problem, the page curve. This is sometimes called, so the page curve would be the curve of the fine-grained entropy that we expect if black holes are following a unitary evolution. It's this curve here. And the white curve is the Hawking curve. So this is the Hawking curve. And the blue one is the page curve. Okay. Very good. Now, so we'll start gearing up to calculating this page curve, and we'll discuss how we can calculate using semi-classical gravity the page curve. So there is actually something wrong in the way that we were thinking, that we discussed here so far, the entropy of radiation. And we'll see what the correct way of computing this entropy of radiation is, using gravitation formulas similar to gravitational thermodynamics. Okay, so we'll start doing that. And in order to get to that result, we'll need to talk more about von Neumann entropy and how to calculate von Neumann entropy in gravitational systems. Well, maybe I can just come here. So von Neumann entropy, so if you have a quantum system characterized by a density matrix rho, von Neumann entropy is given by this formula. And it has the interesting property, well, this important property we just mentioned. This is one of the properties. Another property is that it has some kind of quantum information meaning, similar to the classical information that the diagonal. So if you have a classical probability distribution, there is a similar entropy that you can define, which is called the Shannon entropy, minus p log pi. This entropy tells us what the capacity of a channel where we use letters, let's say, distributed with these probabilities, or elements that are distributed with these probabilities. We can send information at a rate that is set by this. If we have a quantum channel and we send systems that are drawn from a probability from a density matrix rho, then we can send this amount of quantum information. So it has that quantum information meaning. And that quantum information meaning comes from repeated uses of the channel. And in particular, this entropy can be defined for any system. It doesn't have to be a system that is in equilibrium. So you can have an exploding thing and calculate the density matrix. You can calculate this entropy. Okay. It could be time dependent. It doesn't have to be stationary, and so on. Now, for equilibrium systems, so if you have a system which is in thermal equilibrium and has been in thermal equilibrium for a very long time, in contact with the bath, and you decouple it with the bath, then that entropy will be equal to the thermodynamic entropy, and the density matrix will be, for example, proportional to the identity if you're in the microcanonical ensemble, or proportional to e to the minus beta h if you are in the canonical ensemble. Okay, so for these two particular cases, the two-wheel system has been in equilibrium for a long time. Now, it's very important to distinguish the entropy that appears in thermodynamic considerations from this fine-grained or quantum entropy. Let me just mention different names for this entropy. So this entropy we discussed here is called fine-grained. Quantum entropy, or von Neumann entropy, etc. So it has these various names. Okay, so it's important not to confuse it with other kinds of entropy, in particular, not to confuse it with Boltzmann entropy. So let me just emphasize the difference between fine-grained entropy and Boltzmann entropy, which is something where the dry ones. Let's see. And we'll discuss that in the context of an example, just to understand very clearly the difference between the two. So we'll imagine you have a box of gas. So we have a box, and we have a little box inside the big box, and we have some gas in the little box, okay? It has some initial density matrix rho initial, which is the density matrix of this gas here, and it has some entropy S initial, some von Neumann entropy S initial. Now we open that little box, and the gas will spread throughout the big box. So after a while, we'll have something that looks like this. And this process of opening is just a unitary transformation. So there is some density matrix rho final, which is related by a unitary transformation. And therefore, it's entropy final, von Neumann entropy final. The final one is equal to the initial one. Okay? This is true for the von Neumann entropy. Now, in this type of process, when Boltzmann thought about it, and when we talk about it in the context of thermodynamics, we normally say that the entropy increases, okay, in this process. This is what's called an irreversible process, where we normally say that the entropy increases. So there is the Boltzmann entropy initial, which was equal, let's say it was equal to this if this was in equilibrium. That's Boltzmann initial. But here the S Boltzmann final will be bigger than the S Boltzmann initial. Okay? I gave you the explicit definition of the von Neumann entropy. I'm not giving you the definition of the Boltzmann entropy. I assume you maybe know it, but the Boltzmann definition involves some kind of coarse graining. So you are averaging a little bit, and you are kind of only looking at a subset of the observables, not all the observables. And that is related. That coarse graining is responsible for the fact that it rises. Okay. Very good. So is that clear? Okay. I hope this is very clear. Okay. So we will now focus purely on this quantum entropy or fine-grained entropy, and not on the not on the Boltzmann entropy. So we will not need the precise definition of the Boltzmann entropy in general. However, if we go back to the problem of the collapsing black hole, so let's discuss the collapsing black hole. And so again, picture of the collapsing black hole. We have some initial entropy that we could calculate on this surface, let's say. That is the entropy of the star. So entropy initial, let's say von Neumann, is the entropy of the star. We could calculate either the coarse grain entropy or the fine grain entropy of the star. Could be equal or different, but we could calculate them clearly. After the black hole forms, we could calculate the Hawking-Bekenstein entropy, including the entropy outside. I draw this line so to emphasize that the entropy outside is computed here. Notice, by the way, that it doesn't matter which slice we pick, because they're all related by unitary transformation. Okay. So we could calculate the entropy outside, and we'll get some much bigger value than the entropy of the initial star, typically. So the entropy of Bekenstein and Hawking will be much bigger than the initial entropy of, let's say, von Neumann. Okay. Okay, so now we are saying that if that central dogma was correct, then this evolution should have been unitary. So we would have expected that the entropy just after the black hole forms, before it emits significant amount of radiation, it should have been equal to the initial von Neumann entropy. Okay. So the von Neumann entropy after forming, after the von Neumann, we expected it to be the same as the von Neumann before. Before, and in particular, equal to the entropy of the star. Right? So this is what we expect for the von Neumann entropy if unitarity was correct. This is the Bekenstein-Hawking entropy. So what we conclude from this is two things. Well, one is that the Bekenstein-Hawking entropy is not well. Either it's equal to this, and then the central dogma is incorrect. But the favored interpretation is that the Bekenstein-Hawking entropy is actually similar to the Boltzmann entropy, where we coarse-grained over something. And so, but the question is, how can we calculate from gravity this von Neumann entropy? And the interesting thing is that we'll discuss some formula, some new gravitational formula that can compute these von Neumann entropies. It's a formula that first started by Rune Takayanagi and then improved by various authors to describe now this formula and discuss some of its properties. Have you all seen this formula? Yes? Who knows about this formula? The formula I'm about to mention. Oh, okay. Not so many people. Okay, so if you have some gravitational system, so in the particular case, for example, of the black hole, so the von Neumann entropy is defined to be the following. So we take the area of some surface x over 4g Newton, and we calculate the entropy outside on some surface sigma x that comes from the surface and goes to infinity or some place very far away. Let me draw it. The black hole be a hole that one we were. Going to some point surface, because remember, a point here is also a surface in the sphere that we are not drawing. Okay? So we have this surface here, and we can move it. It can be outside the black hole, inside, wherever. And for any surface x, we calculate the area of x and the entropy. Again, this entropy does not depend on the slice. And then we extremize this over the choices of x. So we find an x such that this is an extremum. So it's typically a minimum in the space direction and a maximum in the time direction. So we move this. There are situations where there are more than one extremum. In that case, we minimize over the possible extrema. Okay, so that's the final formula. Okay. The initial classical version of this formula, where you ignore this, was simply the area of the surface x. Once you include the quantum corrections, we have to put this in. It's better to put it in just from the very beginning. Okay. Now, the idea is that this formula is the formula computing the von Neumann entropy. Notice that x is not the area of the horizon. So the area of the horizon is a possible x. We could put x at the horizon, but we could also put it somewhere. We're always minimizing, so this entropy will always be essentially by definition smaller than the Bekenstein-Hawking entropy, right? Because the horizon was a possible x, so this can only be better. Okay. Now, so we'll present in a moment, maybe next time, an argument for this formula. But before presenting an argument, let's see how the formula works in some examples. So first, let's go back to I guess we had the picture of the evaporating black hole here. And so now, in blue, we are going to draw the, so we had the Bekenstein-Hawking entropy, which is what I was erasing now. And now we're going to discuss the computation of the fine-grained entropy. So let me, we could imagine computing it, separating the system into an outside and an inside by some imaginary surface, as we were discussing here. And so there is something outside we are not computing. We are computing the entropy at various times. So at some initial time, it's something. And now we want to compute it at some later time. And then we can take the surface x. And in this particular case, the minimum x is to go all the way to r equal to 0. So x is at r equal to 0. And in particular, a of x is 0. Okay? There is no area term. And on this surface, we have an entropy, so if we don't have much radiation having gone out of here, or if we have some reflecting boundary conditions, the entropy on this slice is equal to essentially the entropy here. So we get that the Foy-Neumann entropy gave us the entropy of the star, which is exactly what we had expected. Okay. Good. So that's one good thing about this. So it's simple case. Now this might make you think, oh, maybe you always get the entropy of the full slice. However, we could consider the situation of the eternal black hole. Maybe let me draw an eternal ADS black hole. So in this case, if we start computing the entropy at some time here, again, we'll have the surface X. So let me start here. The area of the surface, if we move along the space direction, acquires a minimum at this point, right? So it's possible that this point might be special because it's a minimum in the space direction, but it's also a maximum in the time direction because as we go forwards in time, it decreases, right? So this point is an extremal surface, okay? And then the idea is that in this particular case, the entropy is just the area of the surface plus the entropy outside. And so this is a case where the von Neumann entropy is actually equal in this case to the Bekenstein-Hawking entropy, okay? The area of the horizon plus the entropy outside, okay? Good. So in this case, they are equal. And remember that if we look at the right system here, we can think of this space-time as a black hole in thermal equilibrium. Remember that it was related to the Euclidean black hole, which was, again, representing a black hole in thermal equilibrium. It's the analytic continuation of that. OK, so here we saw two examples. Can we see some further examples? Well, for that, let me remind you how we can think. There are no dry. Where are the dry? Remember we were talking about the Euclidean black hole last time? So we are drawing it as a cigar. Let me now draw it as a disk, just looking at the cigar from here, right? This is the circle in time. So we are evolving the system in Euclidean time over a circular time. And now let's imagine we evolve it in Euclidean time only up to this point, so only half. And so if we cut the evolution here, then this moment is a moment of time reflection symmetry, and we could continue the evolution in Lorentzian time, and we get the just the future part of the black hole spacetime, of the eternal black hole spacetime, or the wormhole, Schwarzschild wormhole. So this we can view this as a way of preparing a state. So we have, if this was in an ADS situation, this evolution is e to the minus beta over 2h. This is a matrix, but we can view this is a matrix with two indices, right? And we can view that as an entangled state in two copies of the Hilbert space. And that entangled state, if you reduce it to the right side, will give us the thermal state. This is called the thermophile double state. It's a state that if you trace one side, you get just the thermal state. OK, and that, well, will give you this entropy. But we can modify this evolution by adding some particles. Here we can add, let's say, modify the boundary conditions, add gravity waves or any other kinds of waves that go into the interior here. And what that implies is that the black hole will get will have the two causal horizons will now not touch each other, so they will come up to here. And we'll get the Lorentzian black hole, which will contain some matter inside. Okay. So in this type of situation, when we go and compute the von Neumann entropy, we'll find that the extremal surface is sometimes called quantum extremal surface. Will be somewhere here in the interior behind the black hole horizon. Yeah, let me draw the full Lorentzian spacetime. So in a time-symmetric situation, we would get a Lorentzian spacetime of this form with matter in the interior. So it's a situation where the exterior of the horizon, so these are called the causal horizons, are very distant from each other. They could be very distant from each other. And the extremal surface could be some point here in the interior. So let me call this the area of the extremal. And this typically will be smaller than the area at this point 1. And because of the area theorem, that will be smaller than the area, or equal than the area far in the future after the black hole settles to some final state. Okay. So this is a case where we have very different areas, and in particular, the entropy, let's say the quantum corrections are small, then the von Neumann entropy will be very smaller than the thermal entropies, but still non-zero and given by some non-trivial area. Okay. Now, there's one final example that I would like to mention. And this example has a long history. It goes back to Wheeler when they were trying to understand the interpretation of black hole entropy. So there was some idea. There was the idea that the entropy could be interpreted as the entropy of what is inside the black hole. What he said was the following. So if we take the Schwarzschild wormhole, which is this solution, but let's say we have the flat space version, or it could be also the ADS version. This is a solution that joins that at t equal to 0, we have a space-like surface that has roughly this geometry. So two asymptotic R3 spaces, or maybe ADS spaces, they are joined by a wormhole. That's t equal to 0. At later times, this wormhole stretches and collapses. Okay? Is this familiar, or am I going too fast? No response. Maybe I'm going too fast. Okay, so let's say we're leaving this space-time. And this whole thing will develop into a black hole. So from the point of view of the observer here on the right side, there will be a black hole. And this is somehow maybe some kind of interior. Of course, it's non-compact. But we could replace this space by a closed universe. That's what they said. And in this closed universe could be very big. From the point of view of the closed universe, this will also evolve into a black hole, right? But here we can put all kinds of matter. We can put, I don't know, a big sphere full of gas and a thermal state. And this sphere could be very, very big. So the amount of matter here would be bigger than the area of this cross-section in the horizon. So this is a situation where the entropy inside, let me put inside in quotations, is much bigger than the area over 4G Newton. So the question was, what are we to make about this? Yeah, I'm about to finish. So what are we supposed to say about this? Now, this is only a puzzle if you think that the black hole entropy is computing the entropy inside. But the black hole entropy is not computing the entropy inside, it's computing the entropy as seen from the observer outside. Okay? And in particular, if we compute the von Neumann entropy in such a situation, starting from the outside, so we're an observer outside, we try to compute the von Neumann entropy. There are two surfaces that we could consider. A trivial surface here, right, where the entropy would be this. This is an extremal surface. And there's another one where we cut somewhere, there is some other extremal surface around here where the entropy is. And in this case, there are two possibilities, and we have to choose the minimum of the two, so we choose this one. So this will be the true S von Neumann in this situation. Okay. Now, there was the idea that there was a bound. Well, people sometimes talk about this bound, that the area should S inside, that the entropy inside some area should always be bounded by the area. Okay. Now, we don't need this bound. In fact, it's not true in this situation. And this prescription always makes sure that with this prescription of the entropy, this situation never arises. I mean, in the sense that this entropy is never smaller than the general. I mean, it's never bigger than the generalized entropy. It's always smaller than the generalized entropy outside that surface. Okay. So whatever happens inside does not matter for this formula. So all we care about is what happens outside. So, okay. Okay, I'm done. Yeah.
We should throw all the entropy bounds away.
Yeah, we have better formulas now. Well, there is one context in which we don't have better formulas, which is in cosmology. So we don't know what the right formulas are. And actually, this the one, let's say, if you wish, defect or problem with this formula here is that it assumes that there is some asymptotic region where you can do arbitrarily complicated observations where the calculation is anchored in this asymptotic region. And people have discussed possible generalizations. In fact, there are some conjectures in the literature and some ways of defining something analogous for finite regions. Any other questions? Yeah, sure. Yeah.
So in what sense is that a von Neumann entropy, in the sense that what is the density matrix corresponding to this entropy?
Good. That's a good question. We should have asked this question while everyone was. We'll discuss that next time. So it's similar to black hole entropy in the sense that it is supposed to be the entropy of something, but the density matrix is not explicit. But it has all the properties of von Neumann entropy. Yeah. We'll discuss. I'll try to be more clear and answer your question next time. It's a good question that I have not explained clearly.
How can I understand that in this case it's actually the von Neumann entropy and not, because for the collapsing matter there was a difference between the von Neumann entropy and the coarse grain entropy.
Yeah.
Whereas in this case they're the same.
In this case they are the same, and in that case they are also the same. They are also the same.
How can I understand intuitively maybe that this case is more similar to the black hole rather than?
Well, I mean, in this case, the von Neumann, the coarse grain entropy is just the area of the horizon. It's the coarse grain entropy as seen from the outside. It's just that you should have never thought that the thing that you should not think is that the black hole entropy of any kind, for Neumann or not, is always includes the entropy of what is inside.
Okay.
So that is a wrong statement. In some cases, it's true. So, for example, for the collapsing black hole, we saw that it included the entropy inside it. This is the case I discussed. But this distinction will be important for what we discuss. Yes. So the covariant entropy bound, the modern version is the quantum focusing conjecture. So it is implied by the quantum focusing conjecture.
Okay.
And
So those are
yeah, again, that was a conjecture, the covariant entropy bound. And so now we have like a better conjecture.
okay, so it's more. Well, this is a stronger conjecture. But
Yeah,
still
because
needs to
it
be
implies.
true.
Yeah.
Okay.